In this last section of notes, we're going to talk about mixtures and states of matter. Starting with states of matter, just as a review, there are three states of matter that we're going to be concerned with in this class, and they are solid, liquid, and gas. And a little bit about shape and volume. Solids have a fixed shape and fixed volume. So, meaning that the shape does not change when you move it from one container to another, nor does the volume change. It has a constant volume. Liquids, on the other hand, when you pour liquid water, for example, into a flask, it will take the shape of the flask, but it will maintain whatever volume it had. So 250 milliliters in a beaker will still be 250 milliliters in a flask, but it will take up a different shape. Gases will take the shape of the container and the volume of the container. So, for example, when you do water displacement and you collect a gas, that gas will bubble up into whatever container that you're collecting it in. And you may or may not have experience with that from a previous class. We'll talk more about it together as a group. But gases will take the shape of a container, so they'll fill up that flask or that beaker or a balloon if you're blowing up a balloon. They'll also take up the volume of the container. Gases spread out to take up the volume of, for example, the room. Gases will spread out and occupy every part of the room. There is no one part of the room that has more gas than the other. There's no place in the room where you will suddenly find a vacuum where there is no gas. Figure 1.11 looks something like this, where it's just showing the differences in the three states of matter: solid, liquid, and gas in the case of water. So you can, this is the macroscopic view. You can certainly visualize that. This is the microscopic view, or the molecular view. In a solid, the particles, molecules are forming kind of this fixed pattern, crystalline arrangement, whereas in water or in the liquid water, the molecules are spread out in between and then when you go to gases, the molecules are spread even more far apart. There's more empty space between them. In this little diagram in your notes, this is just a review of the names of the changes of state. For example, when you go between a solid and liquid and gas, when you go from a solid to a liquid, we say that it's melting. Going from a liquid to a gas is either evaporating or vaporizing. If you go in the opposite direction, down here, gases becoming liquids, that's condensation. And liquids going to solids is called freezing. Then you have this arrow going directly from a solid to a gas is called sublimation. An example of sublimation occurs with dry ice. Dry ice is solid carbon dioxide, and dry ice is, you'll see that gas come off of it, and that's carbon dioxide gas. Another example is mothballs. If you ever have mothballs in a closet, or your grandparents have mothballs in a closet, as my grandmother did, the mothballs are solid naphthalene, and naphthalene will go directly to a gas. It bypasses the liquid stage. It doesn't melt and then evaporate. It goes right to a gas, and that's why those have such a odor as well, because they're producing that gas. On the opposite side here, going gas directly to a solid is called deposition. Deposition. An example of that is frost. We have water vapor in the air. That water vapor, when it hits a cold glass in the winter, and it goes directly from the gas phase to the solid phase, it deposits on the window. That's called deposition. We could also graph those changes in state with a heating curve. A heating curve here has the temperature on the y-axis and the addition of heat on the x-axis. And the point is showing what happens to the temperature as you add that constant amount of heat. And from A to B, where that temperature is going up, that addition of heat is heating up the solid. The solid is, the particles are moving faster, the temperature is going up. From B to C, you can see that the temperature is staying the same. We have this plateau in the heating curve. And that point is where melting is occurring. And when a solid melts, it melts because the IMFs stand for intermolecular forces. Intermolecular forces are breaking between each of those molecules. That's what happens in a change of state, that the forces between the molecules start to break and the molecules spread out. At the point of C is where all of the molecules that would have been, enough IMFs have been broken to convert into the liquid phase. From C to D, then the liquid is heating up. From D to E, once it reaches that temperature at D, that's when it starts to vaporize or boil. And from D to E is where that boiling occurs or vaporization occurs. Again, from D to E, the temperature doesn't change because IMFs are breaking. So this addition of heat, this energy that's being added, is being added so that the IMFs break. And this got cut off on the screen here, but from E to F is just heating up, but in the gas phase this time. Classification of matter. So we are talking about solid, liquid, and gas. Those are the states of matter if we're talking about one substance. But what if you don't have one substance? What if you have more than one substance, mixed together? Then you have a mixture. A mixture are different elements and compounds that are interspersed with each other but not chemically combined. They're not reacting together to form something new, but they're mixing together. You can have homogeneous mixtures, for example, air or salt solution, or alloys. Alloys, again, you should know from the Dime Lab, are mixtures of metals. Those mixtures have particles that are evenly mingled. Properties are the same throughout. Heterogeneous mixtures, on the other hand, are mixtures where they are not evenly mingled, that the properties are not the same throughout. You can find different areas that have different properties. For example, oil and water. We all know oil and water do not mix. They do not mix evenly. That makes it a heterogeneous mixture. Soil, for example, trail mix is another example. Those particles are not the same throughout. You would have different properties depending on the sample that you analyzed. Pure substances are substances that are only made up of one type of atom or molecule. Pure substances can either be elements or compounds. And this is a graphic that shows kind of the difference between atoms, molecules, mixtures, and compounds. Up here we have elements. Elements are made up, cannot be broken down into simpler substances. So atoms, all of these particles are green. They're all the same. Molecules can still be elements. In the example of diatomic elements, things like fluorine, chlorine, bromine, iodine, nitrogen, oxygen, hydrogen. There's more than one atom, but those atoms are the same. So it's still an element, but its simplest particle is called a molecule. Down in the second row, we have mixtures. We have all different kinds of mixtures. In any of these examples, you can see that the particles are not the same. They're different colors. These are mixtures of atoms. This one is atoms and molecules. These are two different molecules. These are molecules and compounds. Compounds have two or more atoms that are different from one another that are then bonded together. We should be able to talk about atoms versus molecules, mixtures, and compounds, not interchangeably, but we should be able to understand and distinguish between those. And then figure 1.14 on page 31 of your Zoom doll book looks like this. It's kind of using a flow chart to break down matter. Is there variable composition? If so, then it's a mixture. If not, if it's all the same throughout, then it's a pure substance. Does it contain various types of atoms? If no, the atoms are all the same, then it's an element. If yes, there are various types of atoms, for example, here, the pink and the green, then it's a compound. And then elements can be broken down into atoms. Mixtures, are there visibly distinguishable parts? If yes, then heterogeneous. If no, homogeneous. In the next part of our notes, we are going to talk about how we can separate mixtures. And depending on the type of mixture, what are three experimental procedures that we can use in the lab to separate the different distinguishable parts.